I'm going to make an educated guess and say that if you're watching this video, you're at least somewhat aware of video games and computers. You don't need to be an expert to know that for a long time, video game consoles, and really computers in general, had low screen resolutions and simplistic sound that ended up defining what that era of software looked like. Nowadays, despite the fact that we have computers millions of times more powerful than anyone who used them back then could even dream of, many video games are still made that emulate that era of gaming. It's reasonable to say that started from a place of nostalgia, but at this point, pixel art with limited colors and chiptune are as much of their own art style as any other way that games look. Thing is, modern game engines just aren't optimized for chiptune. Maybe they don't need to be since we have more storage space than ever, and playing audio files is completely trivial on today's hardware. But I think there's something to be said about file size. You hear about new games coming out that take up hundreds of gigabytes worth of space, and the reason for that is almost always due to assets. Textures take up a ton of space, and audio files take up a ton of space. In my game Jensen Strikes Back, almost a quarter of the file size is dedicated to audio files, and this has bothered me for a long time because chiptune is designed for a small file size. Let's say it's the 1970s or early 1980s and you're designing a computer. Personal computers are not yet widely adopted at this time. If yours is too expensive, you stand to fail in the market. Rather than push raw power, your goal is to get computers into the home. But people still want improvement over the ones they may or may not already have. Video games are a rapidly growing industry, and people want the experiences they can get in the arcade at home. How do you do sound? The answer many arrived at is the PSG, or Programmable Sound Generator. This is a chip that allows software to create sounds out of simple waveforms at different pitches. They're cheap, and as many soon found out, good for creating complex sounds. It's generally agreed that the first game with background music during gameplay was Namco's 1980 driving game Rally X. We don't really need to know much about it other than that it illustrates that game developers wanted to put music into their games, and they were going to do so despite the limited sound hardware. Digital audio had existed for decades, but the high file size made it impractical to use on consumer computers. Enter chiptune. With the power of a chip that will generate sound and memory registers with which to control that sound, it becomes a synthesizer. And because you're not storing audio data, you can make music in very limited file size. Many songs from these games are still iconic because the limited sound forces composers to rely on pure composition to make their tracks enjoyable. And to paraphrase Brian Eno, the limitations of a medium become their appeal once they're no longer necessary. Therefore, people still make music for sound chips that are now over 40 years old. People still make games featuring said music for decades-old sound chips. The question remains, why can't we take advantage of the limited memory chiptune requires on modern hardware? We've been able to emulate older consoles since the 90s. Real-time audio synthesis is trivial, so why can't I write a line of code that will play a note with a square wave? Well, I can. It just requires the use of an audio buffer, or a dedicated area of memory where wave data is written to and read from tens of thousands of times a second. Since there's no dedicated sound synthesis chip, we need to generate audio ourselves. Now, I'm no expert on audio engineering, but I can tell you the fundamentals. Basically, sound waves travel through the air and make your eardrum vibrate a certain number of times per second, and this is measured in hertz. For example, the note A4 is generally tuned nowadays to 440 hertz, meaning that it vibrates 440 times a second. It used to be 432, but we decided in the 1930s to move it up 8 hertz. I'm not going to get into a discussion on musical tuning, but if you want to make your music sound antiquated, try tuning it to A equals 432. Anyway, this means that to synthesize a waveform, we need to play it a given number of times per second. It's code time. Assume that we have a variable phase. When phase equals 0, we're at the start of the waveform. When phase equals 1, we're at the end of the waveform. We need to control how fast it cycles between those two numbers, and the math for this is pretty simple. Assume an additional variable, frequency. This should be the pitch we want to play in hertz. For every sample to write into our buffer, add to phase the frequency divided by our sample rate, which in this case is 48,000. Finally, if phase is greater than or equal to 1, subtract 1 so that it stays between the limits. Now we have the basic math we need, and we can design our waveforms. I have 7 different waveform modes in my implementation. 5 of these modes are basic waveforms that can be generated with mathematical functions for a smooth wave. We've got the sawtooth wave, the pulse wave, the sine wave, the triangle wave, and the integer triangle wave. Before we get into those, something to note is that audio data on a computer is represented using the bit depth. If you've ever heard the term 16-bit audio, that means the audio goes between negative 32,768 and positive 32,767, which are the minimum and maximum numbers you can store in a 16-bit value. This is the digital equivalent of a speaker oscillating in and out when it vibrates, and will be referred to as -1 and 1 for simplicity. The sawtooth wave is very simple. It goes from -1 to 1 linearly. Our formula for this is to multiply phase by 2, giving us a number from 0 to 2, then subtract 1, giving us a number from -1 to 1. The square wave is the most common on PSGs because it technically only requires 2 states. It's called the square wave because it's shaped like a square. This is generated by simply using -1 if phase is less than 0.5 and 1 otherwise. The 0.5 in this case is called the pulse width. Some people, including myself, call it a pulse wave because when you change where it switches from -1 to 1, it changes the timbre. If you've ever heard of pulse width modulation, that refers to continuously changing the pulse width for a cool phasing effect. In my engine, I added a feature to do this automatically. It kind of sounds like the Commodore 64. Now, I'd be lying if I said I remembered how sine waves work mathematically. Fortunately, there is a sine function. Raylib, the library I'm using, more on that later, includes an example program that generates a sine wave at a variable frequency. I just use the math from that, which I have on the screen now. The 2 triangle waves here basically use the same formula, except that the integer triangle rounds down the result of the formula. This makes it sound more like the NES's triangle wave. The formula, as I've implemented it, is that if phase is less than 0.5, go from -1 to 1, and if it's greater than or equal to 0.5, go from 1 to -1. The triangle waves and the sine wave have something in common. If you start or stop them when the final value is not 0, it makes a terrible loud popping sound. What I did in my implementation is start it with the phase at 25% or 0.25, and when the note is stopped, rapidly decrease the volume until it reaches 0 instead of simply setting the volume to 0. This ensures a smooth transition between sound and no sound that eliminates the popping. Another feature of many sound chips is the ability to generate white noise. This is useful for adding drums. This may be the simplest of them all to generate since it's just writing a random value between -1 and 1 every sample. But skilled listeners of chiptune will notice that there's different frequencies of noise. How do you do that? Well, the solution to this is not obvious. I got help from Squiggy, the creator of an excellent program called Wave Tracker, to do this one. Basically, you still write a random sample, but you increase the time it takes for a new random to be chosen. I did this by checking if the current sample is a multiple of the frequency, and if so, picking a new random. This makes sense if you look at the waveforms of the different frequencies of noise. The lower frequency noise looks more stretched out, as it were, than the higher frequency noise. Finally, the feature I had actually envisioned as being the main method of producing sound in this engine, wavetables. This will play a custom waveform you define yourself. Since there's not a mathematical function that can generate an arbitrary waveform, we have to instead store it as an array with each point of the waveform defined manually. This isn't much of an issue, and in fact, it's very easy to read this in as a waveform. Since phase is only ever between 0 and 1, it represents a percentage that we can use to find the correct index of the array. Multiply it by the wavelength, which in this case is 32, and round it, and we simply need to write the value from the array that is at that position. Okay, so now that we're generating a wave at the right frequency, we have 2 more things to worry about before we can get to actually making music. A key aspect of making good sounding music is mixing, so we need the ability to play our waveforms at different volumes. In my engine, I've created a table of 16 volume levels ranging from 0 to 3000, and all we need to do is multiply the volume by our output to get a waveform at a different volume. You might ask why I made it a table instead of simply multiplying the volume by 200. This is so that the volume curve can be changed manually at a system level without having to do further calculations. For instance, if you want to make it an exponential volume curve. The second thing is polyphony. How do we play multiple sound channels at once? The easy approach to this also happens to be perfectly suitable for our purposes. Add all the samples together, and then divide the result by the total number of sound channels, and that will be the final sample we write to the buffer. That's basically how audio synthesis works at a fundamental level. That's also kind of all we need to have in order to make epic chiptune. Everything else is going to be controlled by the music engine, and that's the fun part we're going to get into now. But before I do that, I want to clarify a couple things. First, the music data method I've implemented is by no means exhaustive, nor is it the best, nor is it even the most space efficient. I know I just complained about how much storage space audio files take up, but there's also something to be said about how easy it is to actually arrange the music. Since I haven't created any real tools to arrange music, my format is designed to be easy to transcribe by hand, and it still takes up significantly less space than an audio file, which we'll see shortly. The cool thing with this is that you can design your own music format. Second, until this point, I've been showing code that looks like C. This is because for this project, I've been using C and a library called Raylib. Raylib provides, among other things, cross-platform window management, graphics, and access to an audio buffer. None of the code I've discussed is specific to Raylib or even C, and the concepts will transfer over to anything else that affords you an audio buffer. By far and away, the most popular method of making chiptune music is tracker software. Trackers were developed to provide advanced but memory-light music playback on various computers, and they work by having notes and effects placed in a spreadsheet-like sequence that is then played back a whole row at a time. The tempo controls how long it takes to advance to the next row, and since my system is based on a constant rate of 60 frames per second, I use a timer that decreases by 1 every frame to change the tempo. The format I'm about to describe is basically a compressed tracker pattern with the ability to make some MML-style optimizations. Let's take a look at a sample tracker pattern and discuss various aspects that we need to encode. So we have notes, obviously, and then we have instruments and volumes. The volume is the blue B you see at the top there. We also have note cuts, which are the big bar lines. Blank rows are the ones with 3 dashes that have no information on them. And the last thing we'll see here is effects. All of them, in this case, are SO5. Some of them are on rows with notes, and some of them are on rows without notes. Take note of that. Basically, the player will read in bytes one at a time, and based on certain aspects of the byte, do different things. When the track starts playing, it reads in bytes until it reaches a note or row command. It will set this as the currently playing note, and then continue reading bytes until it reaches another note or row command. All the bytes between should be effects that will apply to the current note, but how do we know that a byte represents a note? This brings us to binary numbers. You've heard the phrase ones and zeros in reference to computers, I'm sure, and I'm not going to get too into the weeds here. Pause to read the screen if you want a short explanation of how binary works. In this next section, I'll be putting a lot of extra information on the screen, so don't hesitate to pause to read more. You can read and manipulate the individual bits of a byte, and so by doing that, you can store a lot of information in a small space. In my system, if the highest bit of a command byte is 1, then that means it's a note. The next 3 bits are used to calculate the octave, which gives us 8 different octaves, and the last 4 bits are used to calculate the note. This technically gives us 16 notes, but since there are only 12 notes in an octave, if the note value is higher than 11, nothing happens. Octave 0 is largely unusable in terms of pitch, so that gives us 14 note commands that can be used for things that aren't necessarily notes, but we still want to treat as notes. Fair warning, from here on out, all of the numbers I'm going to say are going to be in hexadecimal because that will make it easier to explain. So note cuts are an easy one and are represented by 80. 83 is a single blank row, which is used for spacing out notes. 84 is our first command where it has a following byte of data. This means that the player will see the 84 and then immediately read the next byte to do something else. 84 means that the following byte plus 1 is that number of blank rows. Nothing happens on a blank row, so this is just telling the player to wait for that many rows before continuing to read. Skilled viewers will notice that one of the rows in our tracker example has an effect with no note on that row. How do we determine when to apply that effect? The answer is Command 82, or the blank note. This will be read as a note, but it won't change the currently playing note. However, it will let us apply effects on this row. Before getting into effects, the special byte that follows all notes is the one that sets the current instrument and volume. This is one where we split the byte in half. The high 4 bits are the volume ranging from 0 to F. The low 4 bits are the instrument, also ranging from 0 to F. This does mean that there's a maximum of 16 unique instruments. To get around this, my player will allow for 16 different instruments per channel, selected from a global bank of instruments. What do effects look like? So far, I've implemented 3 of them. First, and perhaps most importantly, effect F. This sets the speed, or the time the player spends on each row. By setting it to 6, we will read 1 row and then wait 6 frames before reading the next one, resulting in a tempo of 150 beats per minute. I've made it so this is set per channel, which means channels can have different individual tempi. This is useful for triplets. Effect 17 is a delayed note cut. When set, the player will wait however many frames you set it to before doing a note cut automatically. This is useful for doing note cuts that aren't on the first frame of a row. Effect B is an optimization that is not possible in trackers and has 2 following bytes. When the player reads this effect, it will jump the track position for that channel back to the given index instead of automatically advancing to the next note, and the second byte determines how many times it does this. This lets you repeat a section a set number of times, cutting down on the amount of duplicated data. This format is pretty simple if you look at it from the perspective of it being tracker data. For the most part, it makes it easy to convert from actual tracker data. Now for this song, I didn't actually write the hex code by hand. Instead, I did something kind of stupid that ultimately worked. I used GameMaker, a program whose language I'm much more familiar with, to generate an array with a series of functions, then output it in a text format I can copy and paste into the header file in my C program. I did this because I couldn't think of anything better that wouldn't require taking even longer to debug a separate tool when I just needed some complete testing data. But we can still learn some lessons from this. First, get things done in the ways you know how if you ever want to get anything done at all. Second, and this is my penultimate topic for this video, what kind of tool do you think would be ideal for editing this song data? The obvious option here is of course a piano roll. Just kidding, it's a tracker. Given that this format is based on tracker patterns, it only makes sense that you would want to use a tracker to edit it. I do think, however, that it couldn't really be a traditional tracker with a full frame's worth of equal-sized pattern data because of the looping functionality. There's also some effects, including looping, and some more I have planned that would need to not be limited to a certain size of effect column. A tracker that fully takes advantage of the features of this music format would look and feel strange, but would certainly be worth exploring. A second option is to take data exported from an existing tracker and convert it to the proper format. This is certainly an easier option to implement, but it does mean you can't take advantage of space-saving features unless you do something like reading in effects that mean something special to the converter. This would be super awkward to use, but for the most part still familiar to experienced users of the existing tracker. Also may be a good option, but not really what I'm thinking is a primary mode of editing. The option that I'd like to explore is a macro-based approach similar to how I used functions in my GameMaker program. Macros, by the way, are just short instructions that you define for a computer to interpret as something else. This would be easy to implement and provide the most direct translation from manual data to array data, meaning that it wouldn't be difficult to go back and edit. I haven't yet done this, but this is probably what I'd implement were I to use this system in a game production. Oh, and one last thing. Since I started by ranting about how much of a big deal file size is to me, let's actually look at some numbers here and see how much space we save with the sequenced music system I've described. Wave is not really a fair comparison because Wave is uncompressed raw audio data. You don't use it for music. Just so you know, the player program with the music takes up less than 1/3 of the file size of the Wave file, but again, that's not exactly a fair comparison. Instead, we should look at the OGG. That's a compressed format that is generally the standard format game music uses. It is compressed very well with no drastic quality loss, and is decompressed at runtime, meaning it only uses memory while the game is running. This is a lot smaller, and in fact smaller than the player program. But you wouldn't consider the player program to be part of the song itself. The sound engine would reference the same code to play every song in a game. How much is the music data by itself? I think it's pretty clear what kind of space savings we're looking at here. So what have we learned with this process? Hopefully a lot. I certainly have. I started this video with a fairly aggressive tone, but more than anything, I just hope to encourage developers and musicians to explore utilizing older techniques of producing audio on a computer as more than just an aesthetic. Chiptune is awesome. If I didn't think that, I wouldn't have spent over a decade making it. But as I've spent more and more time learning about the inner workings of older games, I've found that many of these programming techniques can still be useful to us in the modern era, and I haven't found many options for doing it that I'm interested in using. Thanks for watching. I've been Mini Macro Sound, and have a great day.